I guess you wanted me to print out for you. I wish you just printed it out and brought it with you. But I was there getting until the last minute trying to print out your emails. So I think I've got most of them. Some of them didn't print in color, even though the files were in color. There was something strange about the files, I guess, the way they were set up. But in any case, it looks like we've got the screen down. Presumably the projector is turned to laptop here or something. Never occurred to me that this is different than other classrooms, but who's ready to show something? Okay, we got a volunteer. Okay, is there any trick to using this projector? We've never used it before. I'm used to the normal assignment classrooms.
Got to turn it on. Give it. Takes us a minute to warm up.
Okay.
And we have access to a black and white printer, but also
That's okay.
I'll send you the copy of it.
Yeah, I'll remember it in. Okay, so those of you who didn't print it out and wanted me to look in this stack before, so I can refer to yours. I guess you all have got names on them anyway.
So we'll probably need to pass the mic back and forth to the speaker too. So
Well, okay, but I think.
Because we're recording.
We're recording. Yeah. Okay. Go ahead. Here's the mic then.
You don't want to. I'll make you a copy of yourselves if you want.
Yeah, you can look at yourselves on the internet now. That to your belt. The other one to your shirt. And
This is ready to go. So are you up there? Yeah.
Yeah, I'm
You
up
can
there.
control them from here too.
Oh, okay.
So one more. That looks good.
Yeah, that looks all right.
Turn them all out. Get even better quality here.
Cool.
And that's going directly to the feed.
Yep.
Okay, cool. So my name is Nicholas Toothman. I worked on a bi-directional path tracing implementation for my final project. So I'll just make use of what I have here. The first thing I did to warm up was get familiar with just making a stochastic path tracer. So I was messing with absorption settings until I found something that I liked. On the far left is something that was a bit too high. In the middle was where I started to kind of find like an absorption that I was happy with. That gave me decent lighting, and I didn't have to change any of my other settings for my scene. And the right was the same thing, but rendered at a higher number of samples per pixel. So after getting familiar with that, I kind of started looking at like the papers from like Fortune, Veach, who's the other guy? Gabos? Gibus? Gibus. Thanks. Along with the supplemental material in the textbook, I don't know if anyone looked at the pseudocode that they provided in the appendix, but it was a little hard to read. So most of my training on this came from just looking at the theoretical papers and then using what I knew from the path tracing and the section on light tracing to try and formulate something. So my strategy was initially to follow the example that we were given in class, where you have a big collection of BRDFs with geometry and visibility terms, most of which cancel with the probability distribution function underneath, and knowing that one point is visible to another, except for it's guaranteed except for where the paths are supposed to connect. So I tried that and didn't really get the results I was looking for. Sometimes it would come out way too dark or way too bright, and the colors that should be emitted weren't really happening. So I scrapped the original plan I had of trying to use the convenient, the smart code, and kind of do it the stupid way and just calculate that sort of stuff myself, because I could at least get a better picture of what I was trying to do. So my approach was, after finding my path, I was using Russian roulette to get an eye path and then a light path. And I did look at, there was something useful in the appendix. There was a description of maximum numbers, or your maximum path length and the minimum count you want to have for your eyes and your lights. So initially I used their same numbers. They had a minimum of 2 per eye and light and a max of 7 total, but the Russian roulette gave me pretty small paths that were reliable in the end, at least to my calculation. So I just sort of did things as directly as I could. If I was on the portion of the eye path, I was trying to get radiance based, or I was trying to use the radiance, or solve the radiance equation. If I was looking at points that I considered on the light path, I was trying to get light transport from the original emission. So that was the first good image I got out of this, and it only took 10 seconds to render, but because it was 1 sample per pixel, but I was actually getting something that looked like my scene. It was nice. Lots of noise. I was using cosine lobe direction sampling instead of importance sampling or BRDF sampling for the interest of time. But I was getting, it's hard to see because it's a little darker, but I was getting some color bleeding and things from, a good direct and indirect illumination path tracer. So I started trying to fine-tune it, find if I was making my probability adjustments wrong somewhere or using an incorrect term, and would get clearer primitives in the scene, but at a trade-off for more noise. So, and I understand because I was using cosine lobing, you're not getting as clear a picture. You're getting more interference because of that. But I was using Boost for this, and I was getting render times that weren't great, but weren't there for an hour or a couple hours on end. So it was enough to at least kind of see what I was doing right, and eventually what I was doing wrong. So in the time that I was able to contribute to work on this, this is about as far as I was able to figure out what I had done. But yeah, if anyone has any questions, and I tried to be straightforward with this and still made some mistakes. So it happened, and I'll see if I can try and correct them.
Okay. Well, good.
I had
Have you not other images to show? Sure.
these are the same ones. They're just the actual files. So this was 1 sample per pixel. This was I think 4, and this was 16. So I was curious why in 16 I was getting so much more noise, but that was like a big indicator I'm doing something wrong. I need to figure out how to fix this and where it's coming from. So owing up to my own mistakes on this to try and figure out how to improve it.
Okay. Well, if you have time to figure out what the mistake was, send me some email.
Sure, no problem.
Okay. Who else has got a laptop? I think I got email, one of these from you. This Kevin Griffin from Livermore, who's been watching our course so for a while. If you want to talk, flip this mic to your shirt. Oh, did you Did somebody leave their adapter? No, that's one. That's yours. You got 2 of them.
Okay, so it's only 4 slides. So I'm Kevin Griffin, like Dr. Mack said, I work at Lawrence Livermore. My project was global illumination using a participating medium and also incorporating photon maps for the radiance estimates. So since my scene only used diffuse surfaces, only used 2 different photon maps. I used a global photon map for the diffuse surface rendering and a media photon map for the volume rendering. So the the global photon map, it was created in the pre-processing stage. Photons were emitted from the light source and kind of traced through the scene. And those photons, when they hit a different surface, they were added to the global photon map. For the media photon map, this was used for the volume rendering. The photons were traced from the light source, and they had a formula in the book that was based on the extinction coefficient, where it told you the maximum length that a photon can travel before it scatters in the medium. And that formula I used to kind of trace the different paths of the photons and then add those hit positions, whether it's scattered through the volume or it's scattered based on intersecting a diffuse surface. I added those photons to the media photon map based on the maximum length that it could travel before scattering. And then with each photon map, the tracing of the emitted photons was ended through either Russian roulette, or I added a depth constant when I was tracing the emitted photons through the scene to be rendered. So when I rendered the scene, the illumination was split in 2 parts, direct illumination and also indirect illumination. The direct illumination basically used the standard ray tracing algorithm that we use for one of the different homework assignments. The indirect illumination was kind of split up into 2 parts also. It was split up into the diffuse surface rendering and the volume rendering. So this image, you just see the results of the diffuse surface rendering. And if you compare that with the previous image, you can see how the photon radiance in this estimate adds to the scene and brightens it up. The part I'm currently working on is incorporating the volume rendering into the entire scene rendering. So for the volume photon map, I'm using 40,000 photons and 1,000 photons for the radiance estimate. Most of the code is done right now, and I have to tweak the ray marcher. So I'm using a fixed length ray marcher instead of the adaptive ray marcher they talked about in the book. And this was more for implementation purposes. It's a lot simpler to kind of implement that type of algorithm. But this is going to add a lot of overhead to when I finally render the entire scene. And for the volume rendering and the diffuse surface rendering, I was using this cone filter to kind of, so when I gathered the different photons to estimate the radiance at each surface hit or scattering effect, the more distant photons were adding a lot of noise to the image. So this cone filter helped take those distant photons and kind of divide out some of the effect that the farther away photons had on the image rendering. But overall, the utilization of the photon maps actually speed up a lot of the rendering and took out a lot of noise of the diffuse surface rendering. When I just used ray tracing alone, to render a scene like this took a couple of hours to render, and it was still a little noisy. This took a couple of minutes to render after the photon maps were created. So the remaining work I have to do is to do the volume rendering and tie that into all the different, and add it to the direct illumination and the indirect illumination of the diffuse surfaces. And that's all I have.
So email me if you get it done, but before the time I have to turn in grade. Okay. So I'm glad you came to present with stuff so far. That's where I work more many deal with guys before. Something else is that. Great. Okay. you have it good. Okay. You got it. Okay, maybe I forgot to print it out. So thanks for bringing it. Please put the mic on your shirt too. Be recorded for posterity.
Yeah. So I did photon mapping. So that's the final picture. So basically, I have diffuse surface, and then I have mirror reflection, and there is the refraction and caustics, and these are caustics too. So basically, it's a combination of three stuff. That's direct illumination, and then indirect illumination, and indirect illumination is photon map, and then caustic maps. So that's a result of the direct illumination. And then that's just done by standard ray tracing. And then that's the indirect illumination. All the color breeding are from this map. Yeah. And then that's the caustic map. So you can see those highlights from the mirror and the refraction of the glass ball. Yeah, and then it becomes this picture. So yeah, you can see from this blue color breeding are from the photon map. And one problem I'm having is, so this one, for this shape, it's coming from the mirror, and then that smaller shape is coming from the direct illumination. But they should have the same size and strength or intensity. But I think I'm using a different formula, so I will need to change that. Yeah.
Okay, so like I said, if you get it to change formula before my grades are due, please email me.
Okay.
Okay, you have somebody else? Oh, we have everybody here have something to show. Sure. Okay. Yeah, if you don't like the quality of what you printed out, just email it and I can look at it. That's maybe why some of you did. I thought you did it because you hadn't printed it, but maybe you did it in addition for that reason. So I thought I needed to print them all and bring them with me. There you go.
Try just dragging it into the GIMP window. Drag the file.
How about I just show you my notes here? Okay, this is my final images, one of my final images. And I also, I basically implement a two-pass algorithm to simulate global illumination using photon maps. And I also add caustic and perfect mirror effect to the scene. So, so I estimate the radiance for the caustic. So this is my caustic. Basically, I use photon map to store all the estimated radiance. And basically, when I will pick a random point on the right and then send photon ray only to the specular surfaces, and then it will pass through the specular surface. And hit this point, for example, it will pass through the surface and then go to this point. And then when it hit this ground, which is this diffuse surfaces, and then I will store the radiance into the caustic light. And this is a perfect mirror. And this is the same idea. It's when the ray send a photon ray traced to this specular surface. Then it will because this is just a mirror, and this is a glass. So this one won't go through. Instead, it will just bounce to the diffuse surface and store the information in photon lab. I limited my bounces for the global photon map to only 4 bounces instead of fusion Russian delay because, and I think because it is very good quality, the image of very good quality, and then and also the time for rendering is very efficient. And for this picture, 512 by 512 it only takes less than a couple minutes, like a few minutes to do it. And this one is a specular surface material. So you can see this effect is very different than this effect because they are both specular, but this is a specular reflection. This is a specular refraction.
You forgot to put on the mic, so your voice might not have been recorded well.
Okay. Is that okay? My voice?
Yeah.
Yes. Okay. And then this is my second image, and basically it's very similar to the first one. But this is some design issue when I designed this photon map. For example, this one I only use 1 bounce, so you can see there are a lot of noises here. Even though I used 200,000 photons, but you can see there are a lot of noises here. So figure 2 here, this is not enough bounces. This is only have 10,000 bounces, and then and also my search distance is only 0.3. So when I reduce my search distance to 0.15, it will get a picture like that good quality above. So this is a lack of bounces, lack of photons, and also the search distance is too big. And this one, there are incorrect caustic effect add to this mirror because this mirror shouldn't have any caustic effect. So you can see it bounces to a lot paces.
To me, the light bouncing off the mirror should light up that sphere. And then in figure 3, you have light from the light source bouncing off the mirror and lighting up the left-hand side of the sphere. But in your final image, you took that away.
I took that away.
But it seems like the light would bounce off the mirror in the sphere, wouldn't it?
It will bounce, but it will not store in the caustic map, because the caustic map is only storing when it has a refraction, if it is a specular refraction, and the mirror is only doing only is a specular reflective. So when I do the bounce, it will skip every bounce for my photon map. It will bounce, still will bounce to the mirror, but when it bounces, it will not store in the photon map. It will keep bouncing until when it hit another surface. If it is a diffuse, then it will store. Right.
But in figure 3, you have the light from the ceiling. It's bouncing off the mirror and hitting the left side of the sphere.
Here.
But in figure 5 and 6, which are your
right, this one.
It's not showing.
Yes, because I took it away. Yeah, I took it away. Figure 4, this is quite interesting because I took out the direct illumination. Direct illumination, I've done it as usual that we did in the previous classes. So when I do the photon map, photon ray tracing, I basically, the first bound, I skip it. And basically, direct illumination, it will because the reason I skip the first bounce is because I use the direct illumination for the rendering. So you can see this one, when I took off the direct illumination, you can see all these photons displayed here. The fifth one is showing you two problems. Is this ball shouldn't be a mirror, shouldn't be a perfect mirror. It should be like a glass. The lights go through. It should go through from here to here, and then it shouldn't have like a mirror. It reflects all the images around it. And this one is the light. You see the calibration is not good, so the light is too bright here. And also there's another problem here. There's some lights here because I have too much space between the mirror and the wall. So I fixed this problem in my final image. I make this space really small so that it won't have this problem here.
I think we need to stop now.
Okay, that's all over. Sure.
Did I get you right up by email?
Let's find out if this works.
You may have to turn it 180 degrees. Pretty better. Let me turn on the light so you can see what you're looking at. Got it? Maybe you may have to hit a function key to make your graphics card send output to that socket. In Windows, it's usually function FA.
I don't have Windows. It could be because I'm using my integrated graphics right now, so I might have to switch to my discrete graphics. So while I do that, will somebody else do something?
Okay. We got somebody else here then, please? I've got a laptop. I brought it with me. Okay, well, we'll see. I have to power up my laptop. Does anybody have their laptop already going? Okay, why don't you come up, do yours, and then do hers. Did you email me a write-up? Or okay. Try to be quick because I do believe there's another class in this room. We may have to adjourn to my office or to one of the rooms in Kemper. Probably 308, 3 Kemper. going to be available, or most often is.
Okay, so my project was on irradiance caching, and basically the process of irradiance caching is that because Monte Carlo is really expensive, and we all know how much time it takes from Project 3 to calculate just one image, we use the advantage that on diffuse surfaces, adjacent pixels have very similar RGB values, irradiance values, and we do a random sampling of the image first, and then interpolate between the samples to get irradiance for the other points. So initially we do a sampling. What I did was I just did a grid sampling across the image. The red dots are enlarged just to show kind of how it is. But the whole, you can't really see it that clearly on that, but the whole image has, it was like a 64 by 64 grid of samples across to find out what the irradiance location is at the different places. And then we save these, we save the position that it hit, the normal to the position, and the irradiance, and extra factors like the gradient values and the harmonic means and stuff like that into an octree to be accessed later. So for the rest of the pixels, we do one of two things. First we reach out for that pixel and hit a position on the scene, and given that position's hit position and the normal, we check to see if there are other samples from the cache within that radius. And if there are samples, then we interpolate between the samples from the cache to find the irradiance for this position. Otherwise, we run the Monte Carlo calculation for this position as if it was one of the initial samples, and we add it to the cache. So the interpolation is pretty simple. We say, okay, given the radius that I talked about, and given that the normals are not too different, meaning we're not trying to use the irradiance from like the ceiling for one of the sidewalls or something, we interpolate using weights and errors. The equation is a little complicated, so I won't go into it now. And we use the equation to find out what the value of the irradiance is at the position that we want to find the value for. So this was my initial result. It's not really that great. And the problem was that we weren't accounting for a linear change in irradiance, meaning we took a sample and we said, okay, over a disk of 0.5, the color is the same, which obviously is not true because we have shadows and lights and there's a gradient of change. So we use, using Gregory Ward's paper on irradiance gradients, we use the translational and rotational gradients, and we get a final image, which is the one on the right. And the one on the left is using the Monte Carlo method, and they're both 512 by 512 images, except the one on the right took a lot less time. The one on the left was parallel processed on my computer with 4 processors, when the one on the right was only on 1 processor, and it took, it was comparatively faster. Okay, any questions?
My final image, so I didn't really bring, I brought some other images, but they mostly look the same, so I'll just talk about this image. So for my project, I did bidirectional ray tracing. I used the algorithm described in the paper. So for my project, I did bidirectional ray tracing, and I used the algorithm described in the paper. So for each pixel, I generate paths of length 1 to length n. And I used also the optimization described in the paper, which is to reuse paths of shorter lengths in generating paths of longer lengths. And before I did that optimization, it took a long time to render each image because each path was being generated separately. But once I started reusing the paths, then my rendering time improved by like a factor of 2. So that really helped generate better images. And I compared the images generated with and without reusing the paths, and there's pretty much no noticeable difference. So I have this one is using 8 samples per pixel and caching the paths, and this one uses 8 samples per pixel. Once it's still loading. Okay, it uses 8 samples per pixel and doesn't cache the path, and there's pretty much no notice. Oh God. Okay. There's no noticeable difference. Okay, I give up on trying to move those. Oh, okay, there. Okay, well, they look. You can't really tell the difference between them, so it's a good optimization to do. And I also added specular refractive surfaces to mine. And in order to do that, I had to modify the algorithm slightly because with diffuse surfaces, the bidirectional ray tracing works really well because you just generate a random direction in the hemisphere from the point, and then the final step to connect the light and the eye paths, you just connect them, and the probability of that actually having light reflected along that path is pretty high because diffuse surfaces reflect in all directions. But when you have specular surfaces, since they generally only reflect light in one direction or transmit it in one direction, then the probability of actually generating a path that you'll have light reflected along is really low. So in order to compensate for that and make the variance less, what I did is that if my path, one of the endpoints, ends on a specular surface, then I add to the path until I hit a diffuse surface in order to make the variance less. And so that made it so that I could actually get pretty good images. Let me go back to the final one. Where is it? I don't think that's the problem. Okay, there we go. It's back. So that gave me a pretty good image with very little noise. Unfortunately, since it is a Monte Carlo method, to get a good image, it takes a really long time to generate it. So this final image has 512 samples per pixel. And so it has significantly less noise than the one with 8 samples per pixel, but it also takes about like 5 times as long. So yeah, that's it.
How long did that take?
That one took like maybe about 5 hours.
Oh, wow.
Yeah.
Okay, do we have anybody else who wants to come drive? Okay, why don't we get those two going while we have a computer fired up here? Successful.
Also try this again. Okay.
Put on the mic.
Okay, fine. Is there a slideshow? Oh, presentation. There we go.
Okay, like many other people, I did my project on photon mapping, and so I'm going to assume that everyone listened to the really great explanations beforehand so we can go faster. Here's one of my images. It was
The pink ball is actually using a glossy material, which uses both the Lambertian and the Phong, as we described in class, how you can sample both of those, both the alpha around the mirror direction and the standard Lambertian, and there's a full specular ball in that too, and this just uses a total global photon map with 500,000 photons, 500 per radiance estimate, and 256 rays per pixel. You might not be able to see it, but here is the corresponding projection of where all of the photons hit for the global photon map. I think it's going to be a little bit too light, and this is projected into the image, so it's going to look a little bit brighter where you're further away, but they're evenly spread. Here's another image. This one also has, in addition to the Lambertian and the specular, it has a refractive ball in the back. And so because this had so many caustic elements, I broke it up into a global photon map and a caustic photon map. Oh yeah, and I also used a cone filter to help with the way these looked. So then on the next image, you can sort of see the global photon map with that green square cube, and you can just barely see the caustic map, which is why I included one more image with the refractive ball, so that you can really see on the caustic map how it concentrates the photons, because we're shooting things directly at the elements that we know are generating caustics. And then finally, I wanted to see like multiple lights and colored lights, so I thought it'd be really fun if I did something that looked like one of those popcorn tins with maybe like a kernel of popcorn in it. And so this was 4 million photons with 1,000 per radiance estimate and only 16 rays per pixel, because this is all diffuse. So I like to call this the popcornell box. Yeah, I know. So that's what I did.
Okay, so do we have any other thumb drives? While we keep this connected. Anyone else with a thumb? Yeah, come on up. Can you Dan? Yeah. Okay. See you face to face. Hand me that. There you go. Don't forget you have a form. So.
Yeah, I have a few of them actually.
Okay.
See, did you forget your, is this yours? Oh, is this for the mouse? Oh, okay. The other one on the other side. Oh, good. Okay. How'd you do the slideshow? Was it
I don't know.
Oh, there you go. Okay, so my name's Dan Potter from Livermore. I did Irradiance caching, and how do you get this to stop? It's like doing a slideshow. Let's see. So I just have a few images to show you. This is just a test scene that I did. It's just a, you can't see it very well because the diffuse reflection is it's pretty faint, but this is using the ray tracer we did for homework 3, Monte Carlo sampling. This took 94 seconds. This is like a 128 by 128 image. And using Irradiance caching, it took it down to 19 seconds. And the image doesn't quite look as good, but if I worked a little bit more on the on Ward's algorithm, or maybe incorporating irradiance gradients into the equation, I might be able to get something that looks more like this. But it took a lot less time, and I was able to actually get some sort of diffuse reflection effect using only 2 by 2 subpixel sizes. And this is a picture of the resulting cache entries in the octree for the irradiance method, or for the caching method. You can see it spaces out more on the planar surfaces, and as it gets closer to the sphere, it kind of bunches up. where the distance to the sphere relative to the plane gets shorter and shorter. And that's because of how the weighting per sample is calculated. Basically, the one interesting thing about the algorithm is that in order to efficiently collect samples when you're doing your interpolation, when you store your samples, you're storing them based on the weight that you saw in one of the previous papers. You basically iteratively subdivide your octree until the node size, until the node size is within certain bounds relative to the weighting of your sample. And so here's another image. These are pretty noisy. I didn't want to spend forever, rendering them. But this is also using the stochastic Monte Carlo sampling, and this is using Irradiance caching without gradients, and you can kind of see the pink bleed through on the side walls from that back wall. So it runs 3 times as fast. So pretty good. And these are the cache entries for that. So they're a little bunched up, probably more than they need to be in the corners, but that's all just depends on, there's a user definable parameter that you run the algorithm with, and I probably just need to tweak it a little bit. But that's pretty much it.
Okay, do you have any more thumb drive? One more, okay. Until the students from the next class start opening the door, we'll try and stay here, then we'll move to Kemper. Yeah, they don't do Fridays usually.
Where in Kemper? Because I have a meeting at 2. That's pretty...
Why don't you, you got something to present?
Yeah, but...
Then do it now.
Well, it's not really working, so...
Well, I mean, if you got to leave, show us now.
Okay.
Do you have a write-up of any sort?
The what?
Did you print out anything?
I sent it to you, but I don't think I sent it fast enough.
What's your name? I may have gotten
Jesus.
Jesus. If you sent it right before class, I tried to get everything. Okay, I'll just screw it.
It might have been a bit after.
Okay. Sure, thanks.
Okay, so I worked on bi-directional path tracing. And basically, I tried modeling it as kind of, I looked at the code in the back of the book in the appendix, and it wasn't easy to follow, as Nick mentioned. So I pretty much just did everything from scratch. And this is here's it simulating a regular path tracer. So what I did was I did no light paths and all eye paths. And the results are pretty similar compared to pretty much what we implemented before in the previous projects. So when I started adding light paths, I started getting these artifacts, and it's pretty much not, it's not correct. So I think I'm making some errors on how I compute all of the light paths, and I compare them to the eye paths when I try to correlate them together.
On the iPad, did you have direct illumination?
Yes.
Okay, so there were some that were aimed directly at the light source.
Yeah.
So, as I said to other people who weren't satisfied with their results,
yeah, this is the contribution of, I tried just the light paths, and this is the contribution of the light paths to the rest of the image, and it doesn't look too correct. So those artifacts, I mean, I'm probably just miscomputing something. But
okay, well,
yeah.
send me an email.
Yeah. Okay. Well, I did send an email already, but I will send a follow-up. Yeah.
By whatever the deadline, I think I said midnight Tuesday or something.
Yeah.
Because then I have to create grades.
So I did photon mapping too.
this is what it looks like with diffuse surfaces.
You're Stuart?
Yeah, Stuart. Did I just? Photon mapping with diffuse surfaces, you can kind of see the color bleeding here and here and on the sphere. I calculated direct lighting, and then with the indirect lighting, I used the photon map. This used like 300,000 photons. I also did glass surfaces and caustics. I'm sorry the caustics kind of washed out. I think they were a little too bright. But yeah, glass, caustics. All right, that's it.
Okay, anybody else? Get it right up for me. Yeah, I may have just printed this from your email right before the last.
So I did bidirectional ray tracing, but I put it on the GPU, so I did it with CUDA. It's pretty much the same algorithm you guys have been hearing, I guess. I did have some problems, though. I'll show that on the next image. But I was able to render this one in, like, I'd say around 5 to 10 seconds. So it was pretty fast. So I don't know if you can see it, but there's some slate bleeding on the boxes. Yeah, yeah, it's a little better. Yeah, so I still had some problems with the variance. It still didn't fuzz out all the way. And then here's the next image that I had.
So did you write your own, or did you use the algorithm?
I wrote my own. The only thing I used was optics to do the actual send the rays and such, like creating the stack and all that. I let optics do all that.
So basically nobody actually used the code in the book, did they?
No, it was pretty unreadable.
Okay.
And then here's my other image. I had some problems around the light where some rays were too bright. I'm not sure if somehow, I don't know, but I had some spots up here that I wasn't sure what they were, and the variance is my biggest problem, I guess.
You haven't been able to figure out what is the light flush with the ceiling, or is it?
No, it's right below. Yeah.
Yeah, so I guess
there's something in the edge.
Light rays getting out of the light and hitting the ceiling directly, I guess.
Yeah, but yeah, that's basically my project.
Okay. So was it easy to use optics?
It took me like a week to get a hang of it, but eventually. Also did it. No,
I'm impressed because it's really fast compared to what anybody else has done. That's what happens when you put things on the GPU.
Just open it.
Okay, that's okay. In the middle of the stack.
What?
Can you cook that when you get organized? Cook that to your shirt. That'll work. We'll just look at it.
Okay, I'm Shunren Lee, and I also did a project about photon mapping, and I also use optics, which is a ray tracing engine based on CUDA. So, So I follow the traditional photon mapping method, the two-pass algorithm. So the main challenge is some engineering issue, like the graphics memory is not too much. So I have to tune those parameters to keep the important photons can be recorded in the photon tracing path. Yeah.
So your diffuse photon map is also going through the specular surfaces, and it's a bit of caustic that's getting the red side of the red wall is sort of creating a caustic image on the right of that shadow. Is that what's happening?
I don't think that's the caustic. I believe it's the.
I don't mean from the caustic photon map. I mean just the diffuse photon map, or global photon map, whatever you call the other one. If you keep tracing rays, you trace them by refraction if they hit a refracting surface.
Yes.
So that's what's actually creating that sort of image of the red wall on the right side of the sphere and the green wall on the left side of the sphere.
Yes, since I don't have a special caustic map, I just have a general global map. It already works for caustic effect. And yeah. And the last one is there are some problems around the sharp edge, like the corner or the edge of the boxes. That's about the issue I'm how to estimate the radiance about use the photons nearby, but yeah, that's some future work.
So what do you mean 50 frames?
Since only one picture will have some spotty effects, that's the general problem of photon mapping. So since it can run really fast, like 10 seconds for one picture, so I keep rendering it. And I keep all the pictures rendered in 5 minutes and blending them together.
So you could have maybe got the same effect with that many more photons, but it would take up a lot more memory.
Yeah, that's.
So this is a way of having, having to store so many photons in your memory. Can you go? Do you have one image that is noisy that can show one frame in a few seconds?
No.
That's okay.
Yeah, that's it.
Okay. Anyone else? Did you get everybody? One more person, okay. Did you print out anything for me?
No.
Okay, well.
Final part is automatic, and at first this is my result using 50,000 of products. And someone told me I think the results pretty strange, and someone said that my algorithm is wrong, so I modified to what you save, and this is the current result I get. I still have a lot of work to solve.
Okay, but it looks like it's working. So if you want to continue with it, please send me email as soon as you get it done. Get it done by next Monday. And all it is at 1 point worth of what you've done as you presented today. So let me just turn on the light and do a quick survey. I don't count ads. Who did show anything today? Okay, so several of you still have to send me stuff. And hopefully I'll get it by Monday and you only lose one. But I think the first exam was scheduled that Monday, so I really need to get it, within 90 grade before my 72-hour limit. Okay, well, it's been a fun class. I've been impressed with your project. Sorry we ran late today.